right, this is 7.3 sine and cosine functions, and our objective will be to use the definitions of sine and cosine to find the values of these functions and to solve simple trigonometric equations. This is a very, very important lesson, so take some great notes. Get a hold of me if you have any questions, and again, we're really establishing our understanding of trigonometry today. So, suppose P of xy, so this is just a point P with coordinates xy, is a point on the circle x squared plus y squared equals r squared. Okay, so let's start with the coordinate plane here. All right, and P is some random point in the plane. I'm going to put it out here in quadrant 2 somewhere. There we go. And you guys know from last year that x squared plus y squared equals r squared is a circle centered at the origin with a radius of r. Something like that right there. And P happens to be on that circle. So that is the graph of the relation x squared plus y squared equals r squared. Okay, now theta is an angle in standard position. That means its initial ray is the positive x-axis, and its terminal ray is, well, let's have that ray go through that point P, so the terminal ray is going to form a quadrant 2 angle with terminal point OP, So again, that means we're starting at the origin and we're going through point P right there. All right, awesome. So that's my angle theta right there. Okay, perfect diagram. All right, so what are we going to do with this diagram? X squared plus y squared equals r squared. Again, a circle centered at the origin with a radius of r. So the length of segment OP right here, the terminal ray, would be r. Okay, now definition. This is the algebraic definition of sine and cosine. All right, and last year you used the acronym SOHCAHTOA. And you can still do things that way, but the algebraic definition is much more powerful, and it leads to your ability to answer a lot more complicated questions and equations. So sine of theta will always be the y coordinate of this point on my ray right there, called the terminal point, over the radius of my circle. And SOHCAHTOA leads to that because you could picture now, see this second quadrant right triangle right here? Picture this acute angle right here, and sine is opposite over hypotenuse. Well, what's this opposite length right there? That's y. And what's the hypotenuse of this right triangle? R. That's the algebraic definition of sine. Sine of theta is y over r. And guess what? Cosine of theta is, now SOHCAHTOA, adjacent to hypotenuse, that would be x over r. All right, there's your algebraic definitions right there. So, you're going to see problems like this today, and these are very important problems. If the terminal ray passes through -3, 2, so that's a point on the circle in quadrant 2, find sine of theta and cosine of theta. So if I have a quadrant 2 angle, I'm going to draw a quadrant 2 right triangle, so it's easy for me to see. All right, and let's go ahead and list the legs of this triangle. So this leg right here would be -3, and this leg right here would be my y coordinate, +2. Now I can find the radius of the circle right here, and I can do that with Pythagorean theorem. So radius, that's a right triangle, Pythagorean theorem, a squared plus b squared equals c squared. So my a is going to be the -3 squared, plus the b is going to be my 2, plus 2 squared equals the radius squared. And now let's just solve for the radius of this circle. So -3 squared would be 9, plus 2 squared would be 4, equals the radius squared. So radius, then let's square root both sides. So the square root of r squared is r, and the square root of 9 plus 4 is going to be the square root of 13. So the radius of this circle is radical 13. There you have it. Now I can use my definitions of sine and cosine. So sine of theta is y over r. And let's put the definitions down here. Cosine of theta is x over r, and sine of theta is y over r. So y over r would be, well, what's the y coordinate of my point? It's a 2. What's the radius of my circle? Root 13. And now we need to rationalize our denominator for full credit. So we're going to write that as, let's multiply the numerator and the denominator by root 13 to get 2 root 13 over 13. I hope you remember that from last year. All right. Now cosine of theta. Well, cosine of theta is going to be x over r. So the x coordinate of this point is negative 3. And the radius is still radical 13. And now let's rationalize this denominator. So let's multiply our numerator and denominator by root 13 to get negative 3 root 13 over 13. And there you have it. Okay, if theta is a fourth quadrant angle, so just draw a terminal ray in the fourth quadrant, wherever you want. Does not have to be perfect. And sine of theta is negative 5 over 13. Find cosine of theta. So let's label this diagram with sine of theta being negative 5 over 13. And remember, sine of theta, okay, there's my angle theta, positive angle theta right there. There's my quadrant for a right triangle. And you guys know that sine is y over r. So sine of theta, y over r. All right, so let's say where we'll put things then. So do you agree that this y coordinate would be negative here, and that would have to be the negative 5? And then r, then, the radius of this circle would be 13. Now I need the other leg of my right triangle, my quadrant for a right triangle right there. So let's see, 5 and 13, that's a Pythagorean triple. So some of you already know that this would have to be positive 12. And if you don't know your Pythagorean triples yet, don't panic. We're going to use them so often that you will have them down. All right. But if you don't remember that, you could also find that 12 with Pythagorean theorem. So we're going to go the x squared, that's the 12 we're trying to find right there, would have to be my other leg squared. That'd be a negative 5 squared equal to my 13 squared. And let's solve for x. So x squared would be 25. Plus 25 equals 169, and now subtract 25 from both sides. So x squared equals 144, and you guys know what the square root of 144 is. That implies x would be plus or minus 12. And the plus or the minus is determined by the quadrant I'm in. Okay, that's a fourth quadrant triangle. That means this x would have to be positive. So my x is going to be a 12. Now, I have everything I need to answer this question, cosine of theta. And cosine of theta is x over r. Okay, and that's going to be, well, my x is a 12. That's the x coordinate of that point. And the radius is 13. So cosine of this angle theta right here is 12 over 13. Okay, although the definitions of sine and cosine involve the radius r of a circle, the values of sine of theta and cosine of theta depend only on theta. Now, we've been using r in our definition, and now they're telling us that sine of theta and cosine of theta depend only on theta. And by the way, that's why we write it sine of theta or cosine of theta. That's interesting, though, because r is in the definition. So, here's what we need to know here. X, Y. Let's say that this circle is the unit circle. And that means it's a circle with a radius of 1. So r here equals 1. All right. Now, guess what happens right here? Okay, xy would equal, all right. Well, think about that now. Okay, cosine of this angle theta would be x over r. All right. And so that means that that x coordinate would have to be cosine of theta. And guess what? Sine of that angle theta is y over r. So the y right here would have to be sine of theta. And there you go. Any point on the unit circle has an x-coordinate of cosine of theta and a y-coordinate of sine of theta. That is very powerful. Okay, now because all right triangles that have the same given measure for theta are similar, all right, the value of a trigonometric ratio depends only on the measure of theta. It does not depend on the triangle size. So we're going to verify this statement. Wow, this is big right here. So let's go ahead and do a coordinate plane, and I'm going to put the whole circle there. I cut off my negative x-axis, so I had room to write over here, but it's there. All right, now let's throw a terminal ray into this picture. There we go, nice. And let's think this is a first quadrant angle right there. And so to diagram this, I do a first quadrant right triangle. There it is right there. This is my first quadrant right triangle with acute angle theta right there. And by the way, what do you think the measure of that angle might be? Let's approximate it. And let's think radians. Start working on this. That is going to be about pi over 4 right there. Okay? And again, you'll get better and better at that. Okay, now this is the unit circle right here. Okay, so that means that we've got a radius of 1. All right, and guess what? You don't know this yet, but you will shortly. I already know this vertical distance right here would have to be root 2 over 2. Okay, and we'll save that for a little bit later. All right, I'm just giving it to you for right now. All right, now let's go to work here. Sine of theta. What does sine of theta equals? It equals y over r. Algebraic, y over r. Or you SOHCAHTOA people, it can also equal SOHCAHTOA. Sine is opposite to a hypotenuse. So let's go the opposite over hypotenuse right there. These are the same thing right here because the y-coordinate of that point right there is the leg opposite my acute angle theta. And the hypotenuse is my radius of my circle right there. All right, so what does that equal? Well, let's look at the picture then. It's my fraction, and my y-coordinate is, well, the y-coordinate of this point right here would be root 2 over 2. And what's my radius? It's a 1. So sine of theta in this diagram equals root 2 over 2. Okay, now let's double the radius of our circle and see what happens. There you go. So the distance from this point to that point will be another 1 right there. And there is my new quadrant 1 right triangle. There's my 1 right there. And now let's find this vertical distance right here. Right now I'm just going to call this a y. Okay? Now, let's read what they told us above again. Because all right triangles that have the same given measure for theta are similar, so these two right triangles have the same theta, so those are similar right triangles, meaning corresponding parts are proportional. The value of a trigonometric ratio depends only on the measure of theta. It does not depend on the triangle size. So what we're going to do is set up a proportion based on these two similar right triangles right here. All right, so here we go. And now the smaller right triangle, look at this leg right here, is root 2 over 2 over the radius 1. Okay, I should talk triangle, the hypotenuse of that smaller triangle. And then the opposite leg of the larger right triangle is y. And that radius right there, or hypotenuse of that right triangle, is 2. Okay, well, let's solve this for y. So that implies y equals, well, if I multiply both sides by 2, I get root 2 over 2 times 2, so y equals root 2. All right, awesome, root 2. Okay, now take a look right here. So sine of theta Now we're talking about the same angle theta right here. And when we use this first quadrant 1 right triangle, we got root 2 over 2. What if we use now the similar quadrant 1 right triangle right there? Sine is y over r, algebraic, and that equals, and what do we have here? Well, the y coordinate of this point right here would be root 2, and the radius is 2. We get the same sine of theta. Sine of theta is root 2 over 2, no matter which triangle we use, and that will always be the case. So sine of pi over 4 is always root 2 over 2. Isn't that cool? All right, big stuff right there. Okay, by the way, let's label some points right here. Okay, we already know the y coordinate of this point right here is root 2. What do you think the x coordinate might be right there? Take a conjecture. All right, and look at this triangle right here. Doesn't this look like a 45, 45, 90 degree triangle, which has the ratio 1 to 1 to root 2? Now we'll get into that a little bit later, but this horizontal distance right here, or this adjacent leg to that angle theta right there, would have to also be root 2. And by the way, this point right here, what are the coordinates of that point? Well, the y coordinate you can see as root 2 over 2, and guess what this adjacent leg is right there? Also root 2 over 2. That's just a little extra for you guys to think about. Okay. Well, that's a nice diagram. I wonder if they're going to give me a point here. There you go. All right. So this terminal point is 3, 4. All right there. So this is a quadrant 1 angle, and let's put a quadrant 1 right triangle into our diagram. And the question is, find sine of theta and cosine of theta. Okay. So here's what we know then. All right. What is this adjacent leg right there? That would be a 3. And what is the opposite leg right there? That would be a 4. And I already know the hypotenuse, and some of you might already too, because this is another special right triangle. 3, 4 makes this hypotenuse. By Pythagorean theorem, it would have to be a 5. And that's why they call that a Pythagorean triple, by the way. All right. So, find sine of theta. Well, sine of theta is y over r. And cosine of theta is x over r. So I already know the answers here. Y over r would be 4 over 5. And x over r would be 3 over 5. So you could do SOHCAHTOA too if you want, but I'm really focusing on the algebraic definitions. But you see it right here. Sine is opposite to hypotenuse, 4 over 5. Cosine is adjacent to hypotenuse, that'd be 3 over 5. So the answers are sine of theta, I'm going to use the algebraic definition, y over r would be a 4 over a 5. And cosine of theta, x over r, that would be a 3 over 5. That's how easy this is. All right, hey, another one, but now our angle is in quadrant 3. So let's draw a quadrant 3 right triangle and label it. Okay, so this leg right here would be a -3, and this leg right here would be a -4, and the radius has to be positive. Note x and y are both negative in quadrant 4, but the radius of a circle is always positive. So I'm picturing another 3, 4, 5 right triangle, another Pythagorean triple. So that has to be a 5 right there. And if you don't see that, check it with Pythagorean theorem. So, again, sine of theta is y over r. Cosine of theta is x over r. So, sine of theta. Well, the y coordinate, -4 over 5. And cosine of theta, the x coordinate, -3 over the 5x over r. And there you have it. Isn't that cool? All right, unit circles. We tend to diagram angles on a unit circle because the radius is 1. So like x over r becomes x over 1 or x, and that's why cosine of theta equals x on the unit circle. All right, but anyway, cosine of theta one more time, x over r, sine of theta, y over r. All right, so now let's think about this. Sine of theta equals what? All right, the unit circle is a great way to measure this, okay? Well, sine of theta would be y over r, and the y coordinate at this point on the unit circle would be 1, and the radius is 1. 1 over 1 is 1. Okay, the y coordinate of that point. Okay, now, cosine of theta, I was a little premature there. Okay, cosine of theta, well, think about this now. All right, cosine of theta is always x over r, but the radius is 1. So cosine of theta will always be the x coordinate of any point on that unit circle right there. And again, it's just your definitions, but your radius is 1. So sine of theta is y over r. If I'm on the unit circle, sine of theta is y. Cosine of theta is x over r, and if I'm on the unit circle, cosine of theta is x. All right. Now, by the way, let's think about this. So if sine of theta is y, then in your diagram, let's add this. If I am an angle in quadrant 1, sine of theta is always positive. In quadrant 2, sine of theta is also always positive. In quadrant 3, sine of theta would be negative. And in quadrant 4, sine of theta would be negative. Now, cosine is x. So in quadrant 1, cosine is positive. But in quadrant 2, cosine is negative. In quadrant 3, cosine is negative. And in quadrant 4, cosine is positive. That's a great little diagram right there that'll help you out. Okay, the domain of sine and cosine. Well, what thetas can I use for sine and cosine? And can I just keep going around and around and my angle getting bigger and bigger and bigger? Yes. Could I also be going in a negative direction? Yes, I can. So the domain of sine and cosine would be all real numbers. Theta is in the set of real numbers. How about the range of sine of theta and cosine of theta? Well, range, that would be my outputs, all right? And check it out here now. Look at all the y values here. Okay, do you agree that the range of both sine and cosine would be anywhere from -1 to +1 because that's the unit circle? So y is in the closed interval from -1 to +1. And there's your range. Okay, sine of 90 degrees. Well, again, sine is y over r. This is a unit circle. Look at that point right there. So the radius of the circle is 1. So what would sine of 90 degrees have to be? Well, sine of theta is y over r. So sine of 90 degrees, well, what's the y coordinate of that point? 1. What's the radius of that circle? 1. So sine of 90 degrees is 1. What's sine of 450 degrees? Well, where's 450 degrees? 360, and then 90 more, 450. There it is right there. I have the same terminal point right there. So sine of 450 degrees is also, remember, y over r. So sine of 450 degrees would be the y coordinate of that point, 1, over the radius of the circle, 1, and that's a 1 again. And again, those are co-terminal angles right there, 90 degrees and 450 degrees. Okay, so cosine of negative pi. Well, negative pi, let's see where you guys are. Negative means I'm going in a clockwise direction, and pi would be half of a revolution. There it is right there. And cosine is what? Cosine of theta is x over r. So cosine of negative pi would be, well, the x-coordinate of that terminal point is -1, and the radius of the circle is 1, so that's a -1 over 1, or a -1. Cool. Practice this. You're going to get really good. All right. Did you notice that sine of 90 equals 1 and sine of 450 equals 1? Okay, very important. Okay, we're going to solve sine of theta equals 1 for theta in degrees. So if I'm going to solve for this theta right here, I've got to undo this sine. with inverse sine. So I'm going to get my calculator out, and I'm going to put my calculator in degree mode, and I'm simply going to punch out, well, inverse sine of theta would be theta. Theta equals inverse sine of 1. So everybody, make sure you're in degree mode on your calculator and punch out inverse sine of 1. Make sure you can find that on your calculator. And guess what your calculator is going to say if you're in degree mode? 90 degrees. And we just said that with our diagram, right? But again, we said sine of 450 degrees is also 1. So if I add or subtract 360 degrees from my 90 degrees, I'm going to be at the same theta. So theta equals 90 degrees plus or minus 1 rotation in degrees would be 360 degrees. And I can do any multiple of that plus or minus 360. So I could go theta equals 90 plus or minus, how about 2 times 360 degrees? Or how about theta equals 90 degrees plus or minus 3 times 360 degrees? And I could just keep doing that forever and ever again. So let's do the general solution for when does sine of 90 degrees equal 1. Okay, theta then would equal 90 degrees plus any multiple of 360 degrees. And we call that an n, any multiple. And when you use an n is in the set of integers, and that gives you your positive whole numbers and their opposites to handle the plus or minus right there. All right, there's the answer to sine of theta equals 1. 90 degrees only gives you one angle, but you need to know that there are infinitely many angles, and here's your notation to represent that. Now, what if you're in radians? Well, let's just convert things to radians here. So theta equals 90 degrees in radians. Picture it. That's right. Pi over 2 plus n times, and what's 360 degrees in radians? That's 1 revolution. That'd be 2 pi. And now we like to write this as theta equals pi over 2 plus 2m pi, where n is in the integers. Put some stars next to that and make sure you understand it. Okay, so the sine and cosine functions repeat their values every 360 degrees or 2 pi radians. And that's because you're doing complete revolutions of 360 degrees or 2 pi radians. Okay, so that implies sine of theta plus 360 is going to give me the same output as sine of theta, because I'll have the same terminal ray at theta, or theta plus 360 degrees. And cosine of theta plus 360 degrees will give me the same output as cosine of theta. Okay? We can do the same thing in radians too. Sine of theta plus 2 pi, that's 1 complete revolution. So if I have this angle and I add 2 pi, I'm right back at the same terminal ray. So that's going to be sine of theta. And cosine of theta plus 2 pi radians is cosine of theta. Okay, so the sine and cosine functions are periodic. Periodic. They repeat themselves. All right, sine and cosine have a period of 360 degrees or 2 pi radians. All right, that's what makes trigonometry so useful. They have a fundamental period of 360 degrees or 2 pi radians. It's the periodic nature of these functions that makes them useful in describing many repetitive phenomena such as tides, sound waves, and the orbital paths of satellites. That's big stuff. So, in the summer, I have a little piece of beach property, and this is what I look at every morning. And when I see this kind of stuff, I always think about the tides. All right, when the tide comes up high, this spit, I can't see it anymore. And then when it goes down, the spit's back again. It's really cool. Anyway, you guys have fun with these problems. Do them carefully. Email me if you have any questions. And here's what I'd like you to do. Page 272, 3, 5, 18, 19, 20, 33, 35, 37, 39. And the red questions are formatted just like test questions will be formatted. Remember though, 5 is just as important as any of these for your understanding. You guys have a great day.